All right, great. Thank you, Bren. Yeah, appreciate everyone joining on at 7:30 on a Friday morning. There's other places you could be right now, but hopefully this is worth your while and give you some new information and support you on wherever you're at in your interest with air to water heat pumps. So as Bryn mentioned, this is a session that I presented with a partner of ours from the EEN, a gentleman named Bill Chidsey, who is a wealth of knowledge, an excellent HVAC contractor, technician, human being, builder, who has been doing this type of work for years and is an excellent resource and wealth of knowledge. So Bill and I had presented this session back in April at the Better Buildings Conference. So we'll present it here to you again here today and go from there. So there is nothing I am going to amaze you with, I don't think, here today. No new revelations, new mystifications to come from this. Really what I am aiming to convey here through the content today is just taking a step back and not looking at air to water heat pumps or other heat pumps in general, for that matter, as some unique technology that needs to be carefully considered differently than another type of heating appliance. Essentially, it all comes back to design and understanding the capabilities of the equipment that you're putting into play. So I'm going to try to focus on some of those essentials and basics and talk more about the overall system design as it relates to the equipment. So again, this is really not about the equipment. It's more about looking at the big picture and putting the right pieces in place to get a successful outcome. So what's bringing us to this point of having these conversations around air to water heat pumps, geothermal heat pumps in general? There's a lot of reasons. This is a bigger part of the conversation for space conditioning at this point. Primarily, they're just a good match for the need at this point when we're talking about being able to design homes and buildings for this type of technology, this type of equipment for heating and cooling buildings. The performance of the buildings, as far as the building envelopes go, and the loads that buildings are seeing for demand for heating and cooling, are now well suited and well matched to the output and the capacity and the capabilities of heat pumps in general. The technology of how the refrigerant cycle works and the heat exchange for heat pumps has expanded its breadth and capacity for different climates and cold climates, and that continues year over year, month over month, as far as new tweaks and new advances in vapor injection in the refrigerant process, new refrigerants, or actually I'd classify that as some old refrigerants coming back into favor that will impact the performance of heat pumps moving forward as well. So aside from any political or policy directives or decisions around, moving away from fossil fuels, which obviously is a significant factor, in just general terms here, we're talking about equipment and technology that's highly efficient, price competitive, and smart fit for the purpose for where we're heading with our buildings. So the key concept to really take into account here, to take away with anything related to heat pumps, that is a departure from what we have gotten used to for heating our buildings. We're going to talk about the heating side of this primarily, more so than the cooling, but is that heat pumps are low temperature output devices. They are, when we're talking about fossil fuel fired equipment, we're talking about equipment that puts out higher BTUs at higher temperatures. The refrigerant process moves BTUs, and it moves them in a way that creates a low temperature delivery output. So this was, as I've been saying, the advances in the buildings that we're conditioning have changed the application of the type of equipment that we use in buildings, or we want to match with them. But an older building where there was not attention paid to the performance of the building envelope, required and does require, and a lot of our buildings in the state still do require, high BTU inputs to keep those spaces comfortable and conditioned appropriately. So you need a high BTU capacity heating system in order to keep up with that demand. But again, we're moving in a direction where just by default, we have much better performing building envelopes, and we're obviously putting a lot of focus and impetus on retrofitting existing buildings to become more efficient, not just for this potential transition away from fossil fuels, but also just to reduce overall operating costs, reduce potential damage to the buildings, durability, occupant comfort, and health. So that is a key distinction, though, to being considering the use of heat pumps in buildings, is that we're talking about low temperature output comparatively to what a fossil fuel system might do. But taking that into account, you know, as I said a moment ago, where we're at with the performance of building envelopes is, you know, that there's a good match at this point for the load demand of the building for heating for what the capacity of heat pumps will often be able to provide throughout the heating season. When you're looking at calculating heat loss for a building and cooling load for a building for that matter, you're working around what's called the design temperature. And that design temperature is also referenced as the 99% design temperature, which means the building will see 99% of the year temperatures at or above the design temperature that we're talking about here. So for Vermont, it does vary a little bit based on location and elevation, but -11 is kind of the baseline standard design temperature for heating loads in Vermont. So what that means is that 99% of the year, that building, any of these buildings, will be seeing temperatures at -11 or above. Now, most of these heat pumps we're talking about here, in general, that were cold climate rated heat pumps, inverter driven heat pumps, air to water heat pumps, are going to be able to maintain a load capacity of COP, a performance, you know, efficiency of maybe not 2.0 at -11, but certainly above 1.5 to 2 at -11, and it gets better from there. You know, that efficiency will rise as the outdoor temperature rises as well. So it's that last percent, that small percentage of the year, does need to be accounted for in the design and the efficiency of the system and the capacity. So we'll talk about that a little bit further on. But just as a level set here, you know, this is what we're talking about for design, you know, what we're basing our system designs on to need to be met. And another key factor to take away from today, breaking this out here at the beginning, is that, you know, we're talking about air to water heat pumps as a piece of equipment that will generate heat and provide cooling, potentially provide cooling for a building, just like a propane or a natural gas or an oil boiler or furnace will provide heating input for the building. It's an appliance that generates heat. As far as fossil fuel equipment goes, heat pumps move heat. But that's just the appliance that provides that heating input. The distribution system of how you're moving that heat energy throughout the building is the bigger part of the equation. You know, it's like an 80-20 split here, in my opinion. You know, 80% of the system we're talking about is the distribution and the design and the efficiency of the distribution system throughout the house. The other 20% is that appliance you're using to heat up the medium that you're choosing to distribute heating throughout the building. So we don't often think of the distribution side of the equation as being the permanent asset to the building, but it really truly is. I mean, if you design a building to be hydronically heated with hot water, you know, 25 years down the line, when that appliance that creates the heat needs to be replaced, you're not going to switch out the distribution system at that point. Or 99.9% of the time, you're not going to swap out or change the distribution system in the building. So it should be really considered as permanent and be designed and installed very carefully, because it is as much of a permanent asset of the building as the structure of the building is. Low temperature is really, again, we're talking about designing around equipment. Heat pump equipment, again, is a low temperature heating device, but low temperature distribution also creates the most benefit for efficiency. So if you have a low temperature distribution system in a building, that means that you're going to get the most efficiency out of the heating appliance that's tying into that distribution, no matter if that's a heat pump or if it's a fossil fuel fired equipment. A propane or natural gas condensing boiler will not condense if the input of the distribution side of that system is putting warm water back into the boiler. In order to get the highest efficiency out of a condensing boiler, fuel-fired boiler, you need a low temperature distribution system to be matched to that. So it really is something that we should be designing for at this point in general, no matter what it is you're going to be plugging in as your heating device. And it's something that we can be looking at to retrofit potentially in the existing buildings as well. It gets a little bit more complicated to do with hydronic systems in an existing building because a lot of that infrastructure for distribution is a hard asset in the building. It's hard equipment in the building that can be a little bit more costly to swap out, but it is possible to retrofit to a lower temperature distribution system into an existing building to make this either heat pump technology be the heating input device or to get the most benefit out of a fossil fuel system as well. So we're talking about heat pumps. Heat pumps, the difference between a heat pump and a heating appliance that is combusting a fuel is that the combustion process is releasing heat energy by the method of combusting the fuel, of burning it, whereas heat pump technology is actually moving BTUs and heat energy from one medium to another via the refrigerant cycle, the refrigerant process. So there's different mediums that we can draw from and different mediums we can move to as far as the distribution side goes. So what we're focusing on today is air to water, where we're using air as the heat sink, and then we're moving those BTUs to water for the distribution side of the equation. When we look at geothermal type systems, where we're looking at the heat sink being either water, as in pond or water, source, or ground, and the ground being the fixed asset that you're drawing the BTUs from or rejecting BTUs into from the AC side, you can be distributing that heat energy via air within the building or water. So, an air-to-air is basically your ducted or ductless heat pumps, where you're taking BTUs from outdoor air, and then the heat transfer occurs across that hot refrigerant coil, and you're blowing air across that hot refrigerant coil to distribute those BTUs within the building via air. So coming back to this point, there's nothing special or fancy about air-to-water heat pumps compared to any other type of heat pump. In fact, the process, the components, the refrigerant cycle is the same amongst any of these heat pump technologies. What the difference is here is that we're making an exchange of the heat energy from air, from the refrigerant coil to water. So that exchange of that heat energy comes from the refrigerant coil to a heat exchanger, where that heat energy is then transferred into water. Water as a storage mechanism, almost always as a thermal storage tank, which is then piped into the distribution side of the system to be moved throughout the house. An air-to-air heat pump is you're moving air across that hot refrigerant coil, and the air moving across the hot refrigerant coil is blowing warm air into the room. So that's the difference here, really, in the functionality of what we're talking about. Air-to-water heat pumps have similar design flexibility that geothermal systems do, because we're talking about the same sort of concept here, where you're creating an integral part of the system is a thermal storage tank, and that thermal storage can then be used to be moving that water directly through distribution devices throughout the house, or you can make the heat exchange occur again, where you have a hot water loop, which then you're moving air across to be doing cooling and heating and or cooling, depending on the cycle of the heat pump. So there's a lot of design flexibility inherent to using geothermal and air to water heat pumps for your distribution options throughout the house. So I'll talk about the two different types of heat pump equipment here, as far as the difference between how that heat exchange occurs. Just taking a second to see if we have any questions.
Nothing at this time, but feel free to
Okay.
raise your hand.
All right, I'll just keep rolling here then. There's two different approaches with the equipment from the manufacturer side of air to water heat pumps. There is a closed system, closed loop system essentially, which is a monoblock and then a split refrigerant system. So a monoblock system has all of the components of the refrigerant cycle and the heat exchange from the refrigerant to water in one device that is located outdoors. It's an outdoor unit. So this is where the refrigerant gain and that the refrigerant cycle is housed within the unit outdoors, and then the heat exchange where you have the refrigerant to water exchange occurs in the outdoor unit as well. So everything happens in this one unit in this sort of scenario. What this does mean is that the water side of the system is moving outside of the building. So it does require a glycol mix. Glycol systems do require regular maintenance to maintain the ratio of glycol to water to provide that freeze protection over the duration of the equipment's use outdoors. What it does allow for, though, is that it's a closed refrigerant system that is fully piped and sealed at the manufacturer, so it does not require any field technician in refrigerant to set a system up like this. So there's no refrigerant charging being done, line sets being charged in the refrigerant side of the equation in the field with a monoblock system. So this is the early and the more common type of air to water heat pump that's been on the market. The air to water equipment that's been around for a while. This was the technology that first brought it to market. And so now we're starting to see more products come on the market where we're using split systems. And now what a split air to water system is that this is more aligned with what we're used to seeing with other air to air heat pumps, where you're actually piping the refrigerant. The outdoor unit is simply doing the heat exchange, that one side of the refrigerant cycle, and then the refrigerant is being piped into the building where the heat exchange occurs inside in an indoor unit. So this is rather than the outdoor unit being a fully enclosed refrigerant system, the refrigerant is moving from an outdoor unit to an indoor unit here. So this does require refrigerant piping and evacuation and filling to be done in the installation. So this does require someone with a refrigerant license and that skill set to be able to pipe and install the system. But with either of these, what it really comes back to is then the connection of this equipment to the indoor distribution side of the equation, and making sure that everything is designed appropriately to integrate with the heat pump equipment that you're tying it to. So, between the two, you can have, there can be things to be paying attention to as far as details go that will affect the performance of the equipment on both options here, both on the plumbing, with the monoblock system, you're talking about sweating pipes for, like you would as for plumbing. When the refrigerant side of this equation, with a splits unit, you have to make sure that you're following best practices for leak tight installations so that we're not having an imbalance in the refrigerant between the two sides of the system, and you don't have refrigerant leaking over time. Both of those things will impact the performance of the system overall. So that's the equipment side of the equation. But again, what we're talking about here is looking at this as a system. So it's only one component. It's that 20%, like I said earlier, of the overall system design that makes the equipment work. So what we really want to be paying attention to is the design and optimization of whatever type of distribution system we're going to be putting into the home. So we're going to be talking about two different primary approaches here for air to water heat pumps, which would be either a hydronic based distribution design or a forced air distribution design. Heat pumps in general, we have three different options. You have two whole house distribution systems, which would be the forced air or the hydronic option. So this is where you're actually, tying in a central system to the heat pump and moving heat energy throughout the house, room by room through a central distribution system. And then, the early implementation or application of heat pumps in our climate have been ductless systems or ductless approaches, where that's pretty much a space heater approach. You're not having a central distribution system moving throughout the whole building where you have control potentially over zones and whole house approach. Ductless approach is you're heating individual spaces by individual heads. So again, we're going to focus on the two whole house systems we're talking about here. I personally, I think, this is the direction we're aiming when talking about whole house heat pump systems. Trying to do a well-designed and well-controlled whole house heat pump system with ductless heads, I think has some limitations comparatively to when you look at a central distribution system. So again, just to reiterate here, ductless, we're talking about point source heaters. So these should be considered as you would with another type of space heater, and it's going to condition the space that it sees, quote unquote. So, when we're talking about retrofit applications here too, one factor that certainly comes into play is if someone starts to, a homeowner puts ductless heat pumps into their home, and they have a hydronically heated home where they have baseboard heat, they're not used to feeling air moving across them as part of their space conditioning. So that can have an impact on comfort, even though you're putting in an appliance into the room or into the space that is generating BTUs and technically heating the space. But if you're moving air across the space and across the occupants that they're not used to feeling, that can have an overall impact on comfort. So it's something that can be overlooked as far as people just looking at objective goals for wanting to reduce fossil fuel use or reduce their overall cost of what they're paying currently for their existing heating fuel. But it is something that can impact how and if the homeowner will use the system. And often, integration into the existing heating system can be a little bit challenging. There's a lot more options on the market now for integrated controls to be able to do this switching over between one versus the other. But this is really, again, just baseline heat pump technology here. What we're talking about more today and focusing on with air to water is the whole house distribution options. So when we're talking about forced air systems, there's a variety of different equipment available on the market now to do ducted delivery with heat pumps. The heat pump manufacturers have a variety of different air handler types that can be used, and they can be central or they can be spatially distributed as well, with individual indoor air handlers to move air throughout the building. So these compact ducted air handlers, which you see as that kind of flat rectangular item right there, that's a refrigerant air-to-air type of air handler. And you can use those in individual spaces through the house to condition multiple rooms from one air handler. You can also do a central air handler, which is going to be connected to a trunk and branch or a more traditional type ducted distribution system throughout the building. So one thing to take away here too, as I said at the beginning of this, heat pumps are low temperature delivery systems, and a forced air furnace that's either fuel or oil or propane fired is going to be putting out higher temperature air through that ductwork than what a heat pump would. So this is something to consider as well on that comfort side of the equation. And you can have a heat pump, centrally ducted heat pump system that will be able to maintain the set point in the room by putting out lower temperature air through the distribution system, but that may impact, again, the comfort of the occupants. If it's getting cold outside and there's enough BTUs being put out by the heat pump to keep the building warm enough to meet the set point, occupants still may get uncomfortable because of this lower temperature air that's being moved. So oftentimes we do see installers integrating what is colloquially known in the industry as a toaster into the air handler. And what that toaster is an electric resistance coil, which will boost the temperature of the delivery air being moved throughout the building. So that's one factor that can come into play with forced air systems. Again, it comes back to what the building envelope is capable of too. If you're not losing a lot of BTUs in the building envelope, then a low temperature forced air distribution system can be more than enough to keep the occupants comfortable at that low temperature delivery or lower temperature delivery than what a fossil fuel system would provide. Bringing this up more so around, the application of a retrofit application. We are seeing a lot of heat pump coils being installed in what were previously just fossil fuel fired furnace, just forced air systems. So again, that distribution system can be designed around optimum delivery for the temperature air that is being moved through it. But if you're talking about a retrofit situation, the existing ductwork may not have the ideal design and layout to be able to do the best for what the heat pump could potentially do. So again, distribution and duct design here specifically really do matter for the overall impact on the system comfort for the occupants. So hydronic distribution is another option here for a whole house system. And we do have a lot of hydronic heating in the Northeast, which is unique. The majority of the country is using forced air systems because the majority of the country is a more of a mixed demand climate where there's equitable demand and need for cooling as there is for heating. In our neck of the woods, more of the demand has been heating than cooling. We're starting to see obviously more cooling demand coming into play now. But what that means is we do have a lot of hydronic heating systems already installed, a lot of that infrastructure here in the Northeast. It also benefits us that we do have skilled technicians who know the ins and outs of hydronic distribution in the Northeast as well. And we want to retain that knowledge as much as we can and shed that to the new generation of HVAC installers and technicians to keep these existing systems running and optimized and hopefully modified to meet the capacity and the capability of new equipment as it comes on the market, like heat pumps, but also because there is a notable and significant difference in efficacy and the ability of carrying capacity in a hydronic system versus a forced air system. You can carry a lot more BTUs in the equivalent surface area with water than you can with air. So we'll talk about that in a little more detail here in a minute. But some of the benefits of hydronic distribution is, again, a higher carrying capacity, better distribution efficiency. You really can dial in the design of the system to be putting heat where you want it and how you want it. You can have really tight zone control, individual room by room control if you want it that way with hydronic heating, which is challenging, if not impossible, with forced air systems. Steady temperatures, you're moving the same temperature water through the loop continuously. In a forced air system, there is a difference in output where the terminus of the supply side is relevant to where the air handler is. At the very far end of the forced air duct distribution system, you're going to be getting different BTUs at that end than you are at the closer to the air handler end. The hydronic system, if you have a well-designed and well-piped distribution system, you'll be able to get consistent BTUs no matter where you are in the building. We're not moving air, physically moving air with hydronic systems to provide the BTUs throughout the building, so occupant comfort can be consistent. That lack of air movement is also not stirring things up in the home that could affect indoor air quality as well. And there's a variety of different distribution devices, which we'll show here when using hydronics. So to illustrate that differential between carrying capacity of BTUs when we're talking about water versus air, higher density capacity in water than in air by far. So we're talking 3,500 times more heat energy can be carried in the same volume of water versus air. So a big way of this impacts the overall design in a building is the infrastructure needed to move those BTUs through the building. I think this is a great illustration here from the godfather of hydronics, I would say, John Sigenthaler, of the equivalent surface area needed to move the same equivalent amount of BTUs and how that relates to the structure of the building. You have a 14 by 8 inch sheet metal duct will carry the same amount of BTUs in that surface area as a 3/4 inch piece of pipe. So when you start to think about needing to move distribution throughout the building and the impact it has on the design of the structure of the building, moving water and moving heat through piping has a lot less impact and a lot more design flexibility than what you need to be accounting for in duct design. And you can get really good duct design in a building and really efficient forced air distribution. But in order to do that, it takes careful integration from design stage. Any of this work takes careful consideration from the design stage. And we'll talk about that a little bit further here too. And Bill had a big contribution to the content of this session on that side of the equation, knowing it from experience. But, especially when it comes to, if you're going to be doing a forced air system, because the actual physical infrastructure is as big as it needs to be, you can't just shoehorn that in around the structure of the building. You have to be designing the structure of the building and carefully knowing where you need to be moving what size duct at what place and in what length, so that that can actually be installed as designed instead of having to change the design because of the structure of the building. So all of this really takes into account looking at this as a system, not just distribution and appliance, but system being, everything coming together here, the design of the building envelope, the design of the structure, and the design of all the components that need to come into play to move the heating, cooling energy through the building. Again, if anybody has any questions as I'm going here, just raise a hand, or Bryn can poke me with anything coming up in the chat. So now we're going to talk about getting into the actual mechanism of that heat energy delivery in the building and the type of emitters that will be putting those BTUs into the building. So an emitter is the device that's actually going to be shedding those BTUs into the rooms. So we're talking about baseboard, we're talking about radiant floors, panel radiators, heat exchangers within a ducted system, slabs, etc. So this all has a huge impact on the efficiency and capability of the appliance you're using to heat the building with. Especially with air-to-water heat pumps and water and heat pumps in general. Again, these are lower temperature delivery devices. So we're talking about optimizing the distribution side and the emitters to get to the lowest temperature delivery possible on the emitter side to get the highest efficiency and the most delivery capacity out of the heat pump. Again, this same concept comes into play when we're talking about fossil fuel equipment too. Again, a condensing gas boiler will not condense if you're not getting an appropriate level of BTU exchange on the supply side and the return side back to the boiler. And if the lower the water temperature can be on that distribution side of the system, the more efficient that fossil fuel gas boiler is going to operate. So the old Fossil fuel technology, putting out high BTUs, put out high temperature water delivery. We were talking about 150 to 170 degree water going through traditional fin tube baseboard radiators as well. Old cast iron radiators that were retrofit from steam. We're talking water going through those systems at that sort of temperature, from like 145 to 170 in that range. What we're talking about here for heat pump equipment for air to water or geothermal is optimizing the temperature down between 90 to 120 degrees. And the lower you go with that delivery temperature, the better the efficacy and efficiency of the system overall. So the type of emitter that you use has a big impact then on what temperature you can move through it and what your design options are. So there's a variety of different sort of tables like this you can find online that kind of gives you a reference point of the different types of emitters and where they stand within that hierarchy of delivery temperatures. And this then can help guide what you're looking at for your distribution options throughout the building. Low temperature is important. This is just an illustration to that point I've been making about gas boilers, where the temperature range where that boiler will not be condensing and not meeting its efficiency rating can be the majority, if not all, of the heating range or the heating capacity if you haven't designed the distribution side of the equation to optimize low temperature. So if you have this is just illustrating here that if you have a 98% efficient boiler, but you're tying that boiler into a distribution system that is moving 140 degree water, it's never going to be condensing and you're never going to be getting that efficiency out of the system. It's going to be operating at a much lower efficiency. So once you drop that delivery temperature down, you gain that benefit of the full potential of what the equipment was designed to do. And this has to do with shedding those BTUs on the distribution side. You want a strong delta T between the water heat energy going out on the supply side and then what's coming back into the boiler from the return side. You want to be moving as many BTUs in that cycle as possible to gain the most efficiency out of the equipment. This chart here gives some reference to how the water temperature and the distribution design and temperature can impact the overall efficiency of a heat pump. So there are three different lines here showing 110, 120, and 130 degree water. And the left side of the table here shows what the COP or the efficiency of the equipment will be at those different delivery temperatures and outdoor temperatures. So you can see here that consistently, the lower the delivery temperature, the higher the efficiency of the equipment will be. All right, I'll take a second here, see if anybody wants to pipe up. Any questions, anything from the chat?
Thanks so much, Steve. I think we definitely have a lot of interested folks. Some are already utilizing air to water heat pumps in their projects. Some are just learning about the technology and possibly expanding their services.
Great.
And then others that are looking at the demystification of the technology. So hearing some rumors and wanting to learn more about that side of things.
Well, I hope I can bore you all with simplicity then.
Love it.
That's my aim, is to try to get the outcome being this can be simple, and it really just comes back to intentional design. So
great. And then lastly, I think some folks are just looking at electrification, moving off fossil fuel systems.
Sure. Yeah, we can talk about that. I don't have any slides in here about electrical capacity and considerations on that, but yeah, we can talk about that as well. Yeah, one thing I will say, actually, just as that's prompted me here, is that these are all inverter driven heat pumps. And so these are not hard start appliances, like an old school sort of furnace or boiler, especially boilers where you have large pumps potentially that come on and start hard, meaning they draw a high amperage when they turn on. Um, this type of equipment, it's modulating. So it's going to come on soft and modulate to meet the demand for whatever is being put on the equipment. So you do need to account for enough electrical capacity in the building and service to the building to run everything that you want to run electrically on the house. But these will not, it's not like you're putting in an electric resistance boiler, which is going to have a huge draw and a huge impact. This is inherent to the technology and the efficiency of the refrigerant process and the equipment involved, that these will not dim the lights in your neighborhood when the heat pump comes on to run. So it does allow for some flexibility and integration into existing electrical systems.
Awesome. Thanks so much. Nothing by way of questions just yet.
Okay. Great. Thank you, Bryn. So next few slides just illustrate some of these low temperature emitter options. So radiant floors, we're all familiar with radiant floors. Radiant floors are great. What a radiant floor really offers that's different than other emitter types is it takes the medium, the water, and creates a monolithic heating surface, a concrete slab or a gypcrete. And that's what this middle picture illustrates here, is one of those primary examples of that, where the tubing that you're running and you're running the warmed water through will uniformly heat that concrete or gypcrete here and create an overall warm surface. Similarly with other types of staple up from the bottom underneath the subfloor or above subfloor radiant tubing systems will have the same concept. That tubing is running underneath the finished floor surface and is uniformly heating up the floor. So these are systems that are meant to run at steady state. That's a good match for heat pump equipment as well too. We're talking about steady state efficiency here, so there's not huge swings in temperature in the room or in the space or in the fluid medium running through the piping. We're keeping a more uniform temperature and uniform circulation going with these types of distribution options. There are, again, as I'm illustrating here, different ways of doing radiant floors. And over the years, I think there's not a huge impact on overall performance by differences in the type of radiant floor we're talking about here. Whether it's in the subfloor, below the subfloor, gypcrete, you can get similar levels of efficacy and performance across the different types and different ways of achieving a radiant system. I don't show any pictures here in this content, but you can do radiant wall panels. You can do radiant ceilings as well. There's some differences in the design when doing that. One thing that is inherent though with radiant floors is that you cannot do cooling in these systems. You can't put chilled water through a radiant floor because you have the potential for condensation to occur. So if you want to do cooling and heating with the same heat pump, there are distribution options for that, which we'll talk about here in a moment. Panel radiators are another emitter option, which are pretty common and quite effective. This is kind of like the modern version of the cast iron boiler. You're moving the warm water through a series of pipes, cascading pipes that are in a panel. Some of these are just passive radiant heat from that panel. There are options of panel radiators that actually have a fan coil in them as well, which means that they'll move air across that water loop running through the panel radiator as well. So you can move warmed air through the room off the panel radiator. So these are very common in Europe. We do see a lot of these in play here in the Northeast as well. But these are optimized for low temperature water delivery. Low temperature or high output baseboard. So this is just the lower temperature take on fin tube baseboard. The primary difference here is that you're creating more surface area for that lower temperature water to see, quote unquote, into the room. So, surface area matters here when we're talking about low temperature. That's how you're getting those BTUs moved into the room or moved into the spaces, is by creating more surface area for that heat exchange from the warm water into the room to occur.
Thanks, Steve. We have a quick question if you want to pause.
Sure.
So mini splits can be used for heating and cooling. Can air to water in a hydronic baseboard system be used for cooling as well?
Good prompt and good question. So yes, you can do, and this is one of the cool things when you have this exchange of the refrigerant to water, is you can do a lot of different things on the distribution side of the equation, mix and match. But it does take specific then emitters to integrate into the system to do that. So let's say to that purpose, you could have low temperature, high output baseboard like this throughout the house for your heating side of the equation using the air to water heat pump. The air to water heat pump is maintaining a thermal storage tank, a buffer tank of hot water for this purpose here. And then on the cooling side of the equation, if you want to be doing cooling in the summer, you can have fan coils like a traditional ductless wall head in the home, or there are floor mounted options of this as well. Excuse me. Similar to that panel radiator. Excuse me. And so this is an option for how to do cooling in a home where you still want to use either a radiant floor or other low temperature baseboard as your heating distribution side of the equation. You can also integrate these types of units in the home to do the cooling side, because what's happening here is you have the refrigerant pipe or the water piping moving, coiled through this wall mounted unit or floor mounted unit. And there's a fan coil in there as well too. So what that means is that on the cooling side of the equation, the summer months, that outdoor heat pump unit, the refrigerant process is actually cooling down the buffer tank or the storage tank. So you're creating cool water. The cool water is being piped through these types of emitters, and then air is being blown across that cool water in that piping and providing air conditioning to the spaces. So this is one delivery mechanism for doing cooling and heating. You could do heating with these as well too. Or what's pretty common in geothermal systems is to do a ducted system throughout the whole house, a whole ducted distribution system for heating and cooling, where you have a fan coil unit, an air handler unit with a water coil in it. So instead of having a refrigerant coil that you're moving air across that's moving BTUs, you have a water coil, hydronic coil, where you're moving air across either hot water when it's in the heating cycle in the winter, or again in the summer, you're switching that to cooling and you're shedding those BTUs into the ground or with an air to water system into the air. And you're running cool water through that hydro coil in the air handler and blowing air across it for cooling. So sky's the limit when it comes to distribution design, really is. When it comes to air to water systems and with geothermal systems, you can mix and match, you can rely on one versus the other. You can just condition certain parts of the home for cooling and not the whole house. So it really comes back to understanding what the needs are, what the desires are for the overall, for the occupants, for the building, and then integrating the right equipment, space by space, use by use through the building. So hopefully that answers that question. But just what it gets back to is there's certain emitter types on the heating side that you cannot use on the cooling side. So you do have to be specific in what it is that you're installing to provide that cooling side of the equation. So a key component of an air to water system, and most geothermal systems as well too, is a thermal storage or buffer tank. They're known as buffer tanks in the industry. But really what it is thermal storage. So what the heat pump is actually heating is this storage tank of water. And then your distribution system of whatever type you're integrating is actually piped into and coming from this thermal storage tank. So the heat pump really is only maintaining the water temperature in that storage tank. It's not reading the temperature in the thermostat in the living room and turning on or off based on what the thermostat is saying. The thermostat is telling that buffer tank, that thermal storage tank, to circulate water to make that room warmer to meet the set point. So what the heat pump is doing throughout the season is sensing the temperature in the water tank, the thermal storage tank, and maintaining that temperature. The capacity of air to water heat pumps and their ability to generate capacity down in cold temperatures is more than enough, really, in most any system design to be the sole source of BTUs for that thermal storage tank throughout the heating season. Remember that design temperature I was talking about at the very beginning there, that 99% design temperature. So 99% of the year, -11 or above is what the building will be seeing. And any of the heat pumps that we're talking about here have capacity that will go down to -20 and below. That capacity, output capacity does drop as outdoor temperature drops, just like with any heat pump. There's less BTUs to pull from the ambient air as it gets colder outside. But with the right design and the right capacity factored in, there's enough time and enough storage to be able to maintain enough temperature in that tank to meet whatever the distribution side of the equation is going to see during cold outdoor periods. That being said, too, there's a very small percentage, again, of time of the year that these heat pumps will be seeing temperatures where they will, quote unquote, struggle or not put out as much BTUs, and their efficiency will drop. In those sorts of scenarios, if there is a high draw of BTUs from the buffer tank on the distribution side throughout the house, and the heat pump is not able to keep the set point in the buffer tank, there are electric resistance elements. That's what these two little guys are here on the tank. Those are electric resistance elements like you'd see in a traditional electric water heater. Those can come on and energize and heat the water to maintain the set point if the heat pump is not able to do so. So basically you have backup capacity in the storage tank for the heat pump inherent into the design of the buffer tank. So what this means is that you don't need to have a backup boiler, fossil fuel system to maintain storage temperature here during those cold times of the heating season. These systems are more than enough to be able to meet capacity for the building. Now, again, saying this is because you've designed the house or you've retrofit the house and you've done careful system design and you've modified, if not designed, the building envelope to know that you have a low design load in general. You can't just drop one of these things into an 1820s farmhouse and expect that same outcome because the losses are too significant. You have to be matching the equipment with the need here.
Thanks, Steve. A couple more questions. Can you expand on existing homes with hot air furnaces that homeowners want to replace with heat pump technology?
Sure. I mean, there's a lot to that. Again, you're trying to integrate a refrigerant coil into a air handler that is designed around putting out 120, 130 degree air through the ductwork into the house from the fossil fuel system. And the heat pump will be putting out towards the lower end of that spectrum as far as temperature goes. So, and again, often that existing ductwork is hopefully designed around the capacity and the flows needed and the room by room needs of the fossil fuel system. Because it's a higher temperature system in general, the fossil fuel system, you do have a little bit more of a buffer room by room as far as if the ductwork is not optimized But that's where you can start to see some comfort issues with integrating a heat pump into an existing system. If the ductwork is not optimized for getting the most BTUs out of the delivery room by room, you may not get the most benefit out of the heat pump. You may find that you're relying more on the existing fossil fuel system to do heating than you'd like, whereas the heat pump has the potential to be doing heating down to, low below zero temperatures. The comfort may not be there as much. But if you're talking about integrating a air handler, refrigerant piped air handler to an outdoor heat pump that's specifically designed for that purpose, and the duct system is optimized around that lower temperature delivery, you can fully do, the whole house with the right comfort and the right delivered BTUs with the ducted system. So again, it's back to the legacy distribution, and what modifications would need to be made when you're trying to retrofit heat pumps into an existing system.
Thanks. A homeowner has built a house in the 80s with traditional baseboard emitters. They don't want to convert their baseboards. Are they a good candidate for replacing their boiler with an air to water heat pump?
On the surface, probably not. What you'd need to do would be to actually start with doing a design load calculation for the building. That's the basis for any and all of this, which is what we're going to get into now. But on the surface, I say that because typically, quote unquote, it would be hard to see that being viable. But if you do all the numbers and you do the work and you do the math and you do the calculations and you find out, hey, wait a minute, the original installer here added 20% more lineal feet of baseboard than the house really needed, we can drop the delivery temperature of the water that's coming into this now and still get the same, capacity met room by room. Maybe you can. I mean, in that sort of scenario, you could always integrate an air to water heat pump into the existing system and rely on it for a percentage of the heat load for the house, but not the full heat load. But that's a good segue into where we're going as far as looking at the system design.
And then one more question for the moment. Can a domestic hot water system be part of a heating system, or is
Yep.
it always separate?
Yes, actually, in this picture that you're looking at here, that's what we've got going on. This is, one of these buffer tanks here is thermal storage for the distribution for the heating system. The other one is domestic hot water. So you can integrate both into an air to water system. You do just have to be mindful of what you're designing for to make sure that you're not competing for the BTUs of the heat pump for those two demands at any given time. You want to make sure that you have enough capacity in your thermal storage to be maintaining your set points of your heating system throughout the house at the same time that two people are, showering concurrently after each other and the laundry's going and you're needing those BTUs for domestic hot water heating too. So yes, it can be done. Yes, it's typical, common to be done. It just takes careful design.
Awesome. Well, great questions. Keep them coming. We'll have Steve move on to the next topic.
Great. So yes, great segue into where we're heading here. We're talking about design. What does it take to make a good design and make all of this work together? What you're looking at here is a capacity chart from a manufacturer of what the output of the heat pump is at different temperatures. So we'll reference this in the next few slides. But what we're looking at here to break it down is you've got the water temperature being delivered by the heat pump, what the outdoor air is that the heat pump is seeing, and then what the BTU capacity of the heat pump is at that outdoor temperature, what the efficiency is, the COP. So, and you'll look at this, you'll see 100-degree water temperature, 120 and 130-degree water temperature. And then these are the different outdoor air temperatures for reference and the capacity of the equipment at that outdoor air temperature. The hertz here that's being identified, 90, 60, or 30, is basically high, medium, and low speed of running the equipment. So This is what I'm going to be referencing here over the next couple slides as far as capacity and design and efficiency. But design checklist. So this is where Bill Chidsey and his experience and his content really helped bring the content together here for this session, is being very granular and specific about what it takes to be really accounting for in designing a system. So we're not just looking at this heat pump is rated to do X amount of BTUs at X outdoor temperature, therefore it's a good fit for this home. It's really, you got to do the math, you got to do the work to put the right pieces together to get the whole system to work cohesively. And this is a requirement for air to water design. This is a requirement for geothermal. This is a requirement for fossil fuels. This is a requirement for any design. There was a lot more like room for error, or being a little more loose on this sort of side of the equation when we came with fossil fuel equipment and we had homes that were losing a lot of heat energy. Oversizing was a big factor. We're not at that place anymore. We have to be careful and deliberate in the sizing and the design of the system to get the most benefit for comfort, for efficiency, for durability. So it all comes together. So these are just some of the factors that we're looking at when designing a system. So ventilation sizing. So you need whole house ventilation for any building at this point too. And whole house ventilation means that what you're doing mechanically to provide fresh air for the occupants and exhaust stale air and humidity and pollutants from the home. It's a closed system that's operating on its own accord. Sometimes it can be integrated into a forced air system, but typically you want that system doing its own thing on its own accord. And you have to design that system as well. You have to know how much ventilation you need for the specific building and integrate that into the building. That impacts the overall design of the heating and cooling system as well. The infiltration target is how airtight the building envelope is going to be. The tighter the building envelope, the less of a demand you'll see for heating, cooling. That leads you into your heating and cooling design loads and how that's calculated. Bin data is basically, there's localized data of how many hours of temperature, outdoor air temperature, that locality sees throughout the heating season. That can come into play when optimizing the controls and the setup of the heat pump. This then comes into what heat pump you're going to select to use for the needs of the building and the needs of the occupants. The emitters, what's the distribution design? What are the how are you going to be moving those BTUs through the building? So these are all the pieces that come into the puzzle to come up with the full plan for the project. So you have to have good data. Good data in equals good data out. Get an understanding about what the expectations of the occupants are going to be. That affects, what your distribution options are. Like I said earlier, some people really like having warm air being moved across them from a furnace because that's what they've gotten used to and that's what makes them comfortable. Other people would hate that. So that's a huge decision point in what your distribution system design is going to look like. Taking into account the ventilation needs for the building, the CFM, the building envelope assembly values is a huge component here, and being very accurate and specific to the building design. That has a big impact on the calculated loads for the building and the sizing of the equipment. And then room by room calculations as well. There's a big difference in what a room needs for heating and cooling input when you're talking a, 20-foot by 30-foot living room with 15-foot ceilings and a bunch of windows versus a 10 by 12-foot bedroom, in the northeast corner of the house with one window, so it does that is as much of a part of the equation as the design load for the sizing of the heating and cooling equipment is the room by room loads. That's what you need to be able to design effectively how to deliver the BTUs either by hydronics, by water, or by forced air. Getting to this outcome requires the cooperation and contribution of a variety of people in any project. You know, you have someone who's going to actually do the setup and the commissioning of the system as a whole and dialing all of the pieces in to make everything work as designed. You know, electrician needs to be able to provide the right capacity and the right wiring for the system. If you're doing a system, split system where there's refrigerant involved, you need that technician available. A lot of this is plumbing. You know, if you're talking hydronics, it's sweating pipes, and now, you know, crimping PVC pipes and PEX pipes. But someone with the experience and background to be able to do the distribution side of the equation, whether that's hydronics or duct work, and good duct design in that as well. So this is just an example of what goes into ventilation design. You know, it is specific to the building, where it's located, the number of occupants, the size of the building, how much air leakage the building envelope is seeing. So this is a huge part of overall equation for any building at this point too, is whole house ventilation. That's a whole nother topic and a whole nother training we can get into. But this is something that needs to be defined and designed for and integrated into the system, because it is integral to the overall performance and comfort for the occupants when integrated with the heating and cooling system. The primary mechanism to coming to what size equipment you're going to be using or what type of equipment you need for the heating cooling input of the building comes from the heat load or heat gain calculations that are done. This is what I was just referring to a minute ago, where you're taking into account the building envelope performance, the air leakage, the ventilation requirements, room by room needs. So there are all of these things come together. The ACA Manual J procedure is the industry procedure process to be used for defining design loads for heating and cooling. There's software on the market, there's paper tools, there's a variety of different resources to be able to use that methodology. But it is a methodology that's established by the industry to get all of these factors accounted for when sizing the needs for the heating system. Coming back to the electrical side, we talked about that a little bit earlier, making sure that you have enough capacity in the either existing service to the building and the panel that's available, or making sure that the service side of the equation is accounting for the needs of the system that you're putting into it. So this is just an example of what goes into a Manual J design load calculation for the building. This is kind of showing you where the loads for the building, the heat loss will come from, or heat gain, depending on heating or cooling that we're talking about. So we have, you know, a significant proportion of that heat loss or gain going to windows and infiltration, so the amount of air leakage through the building. And then you can see the walls have an almost equitable component of that as well. Vent ceilings, below grade walls, the impact of ventilation, depending on if it's balanced or exhaust only. So this is just an example of the breakdown of the factors that go into a careful design of what the building is going to see for load, so that you know what equipment you're going to put into the building is going to perform adequately and meet the demands throughout the season. So this is not, you know, thumbnail kind of looks like it fits to me sort of thing. It does take this level of detail. And this is not just specific, again, to heat pumps or specific to air to water, specific to geothermal. This is what should be done with any design for either a new system or even if you're replacing a system. This is the type of effort that's needed to be able to understand that you're getting the right equipment in place. And this is just another example of the same side of things. You know, what the number of annual BTUs are going to different components of the building, the percentages of how they break out. So windows, walls, infiltration being those primary ones that have the biggest impact on the loads for the building. So this is just another way of showing that data from the page before. So getting back to this chart here, performance data. This is where I think there's some data here that really helps to illustrate and answer some of the concerns about whether this equipment and heat pumps can do what the industry and practitioners say it can do, versus others who may feel that we're quote unquote not there yet, or what about this, or the what ifs. So what we're going to look at here is, again, going back to this slide, we're looking at high speed, running the system, at its maximum capacity, medium speed, low speed. Now, when it comes to, both heating system design with something like this that has modulating speed to it, or ventilation design, which can have modulating speed to it, you want to be aiming for the sweet spot here in the middle. You don't want to be having a system that's constantly running at its highest capacity to keep the occupants comfortable, and you don't want a system that's always running at its lowest capacity to meet the comfort for the occupants. So what you want to be doing is aiming for that sweet spot. But we're going to look at what the building sees as far as the demand throughout the heating season. So looking at low speed operation here, and the different capacities that it has at outdoor temperatures. We're looking at the overall, this is the bin data here. So the temperature points that the building is going to see, and then the percentage of the years that the building is seeing those temperatures. So this is on the cooling side of the equation up here, and then the heating side of the equation up here. So on the heating side of the equation, when you look at the overall data, in this example from a project that Bill did, we're looking at 88% of that heating season is going to be at or below the capacity of what the system could do at low speed. And then we jump over to the medium and high speed capacity of the equipment. And we start to see where the range hits for that medium capacity. 11% of the heating season, the system will be at the capacity of at medium speed. And then only 1% of the overall heating season, the system's going to see the demand at that high speed level. So what this is getting at is basically 99% of the heating season, the heat pump is going to be able to operate between medium and low speed and modulate between those two to meet the capacity that the building will need to keep the occupants comfortable. And looking at then what that equates to for efficiency, you can see that at medium speed, we're looking at a COP, an average COP of 1.6. Even at high speed, when we're really kind of getting to those coldest hours, the COP is 1.32. And then if we look back at this other slide where we're getting into the lower speed capacity, we're looking at a COP of 3. So this kind of proves out that in the data that even at that 1% of the heating season here, that's going to be very cold out there. I forget what the design, I don't recall off the top of my head what the design load was for the building here, but this is the BTU capacity here of what the heat pump's able to do at these outdoor temperatures. So the lowest, based on the bin data that this building's going to see, is 0.2% at minus 13 degrees. That's 0.2% of the heating season is going to be minus 13 or below, 12 hours roughly. And the heat pump's able to generate 21,000 BTUs at a COP of 1.3 when it's 13 below zero out. And so if the system's designed and the design load for the house at minus 13 is 21,000 BTUs or under, the heat pump's going to be doing all of that demand at that temperature. But even if the, design load at minus 13 for the building is 28,000 BTUs, again, you have those electric resistance elements in the buffer tank, which will balance out the shortcoming of BTUs potentially from the heat pump to keep the distribution side where it needs to be for the temperature water going throughout the building. Take a quick pause here for any questions from that. Okay. Well, I'm going to end here with some examples of system designs and distribution designs and how that all, again, needs to be accounted for from the beginning and comes into play. So, you know, it's not often and not typical to see the level of design schematics and plans in residential construction that you would see in commercial. Whereas in commercial, you're going to have a whole mechanical set of drawings, which actually shows you where the distribution of the heating, cooling, ventilation is going to be through the building, and specifically what each component of that is going to be per circulator pump size, per location, for piping size, for duct size, for et cetera, et cetera. So when we're talking about residential construction, someone needs to be accounting for this, and someone needs to be either individually or as a team understanding to the same level of detail what would already be specified in mechanical plans in a different, a commercial type setting. Not to say that this doesn't happen in residential design. It certainly does, but it's not quote unquote typical is what I would say. But you still have to, again, account for all of these things. So this is just an example of what some of those things need to be identified as and where they're going to be accounted for in the design of the building and how the building is going to be put together. The location of equipment related to where it needs to be moved through the building. Is the mechanical room big enough? Is it in the right location? Not just based on aesthetic design, but is it in the right location to meet the needs of where you need to be putting distribution components throughout the building? You know, where the grill locations are. If it's a forced air system, has a huge impact on how well that system is going to condition the rooms as designed or as planned. So making sure that that's all accounted for and there's not competing interests. Once the building is built or is underway, it's really important to have this stuff understood and if not defined on drawings at the beginning, at design stage. So really integration with the framers and the framing side of the equation should be integrated at the outset, having design meetings where everyone who has a role to play in the project for putting it together can come together and look at all of this. So it's a lot of details that should be accounted for. It doesn't need to add to the complexity of the building. It actually, I think, creates more simplicity than it does complexity. Because if you get everyone on the same level playing field and the level expectations at the up front, and you do all of that problem solving on paper, people get a lot less upset when you can, fix a design problem with an eraser than you can with a Sawzall. So it's a lot better to take the time at the front end to put all of these pieces together to optimize the design and the outcome and make the flow, the process flow, the project flow go smoothly. So again, this is just reiterating that need to get everyone on the same page and make sure that no one's having competing interests or frustrations as the build proceeds. So this is just a schematic example of, a typical system you could see installed with an air-to-water heat pump. So this is a split refrigerant system where that heat exchange is occurring inside the building. So this is a refrigerant piped unit from the outdoor unit to the indoor unit. This is utilizing a buffer tank, which is, you can see here that the heat pump is feeding this buffer tank. So the buffer tank is isolated, or the heat pump itself is isolated from this distribution side of the equation. So everything is fed off of and controlled from the manifold feeding to the buffer tank. And in this example, you've got multiple different panel radiators that are fed throughout the house, home run back to a manifold. So this is not a pipe system, looped pipe system throughout the house. This is individual home runs back to a manifold where you get very specific control over the delivered BTUs and the flows necessary, because there's different flow capacity for this panel radiator right here than there is for this one. That's controlled in this type of a system. And this is where you can also, you have 5 different emitters in 5 different spaces. You can have 5 different set points in this sort of scenario. And this is a system, again, you don't see any other boiler or fossil fuel type equipment tied into it. This is relying on the heat pump. And again, in this scenario here, in this buffer tank, you have a 9 kilowatt electric resistance element to back up the heat pump if it's ever needed. And as was asked about before, and this is the potential with these types of systems, is you can have mixed distribution types and emitters throughout the house. So you could have, this is going a bit overboard, but it's illustrative of what is possible. You can have an air-to-water system feeding the buffer tank that is then doing radiant heat in one room, panel radiator in another room, a fan coil, a ductless quote unquote wall unit in another room, low temperature baseboard in another room, and then an air handler in another space. This can all be done. This is highly complex and is not typical, but it just is illustrative of the flexibility that you have in distribution types when using this type of system design. And finally, just some pictures and illustrations of equipment in play here. This is the SpacePack split inverter system. This is the system I have installed in my house. So this is a refrigerant pipe system, outdoor unit with 2 fans to move. This is basically one big jacket here of refrigerant piping, and the 2 fans moving air across that piping for the heat exchange. This is the indoor unit. This is where that refrigerant to water heat exchange occurs. This is our buffer tank. So everything is a very simple design, just 2 zones, but we have room by room temperature control. So, and everything, all of the components as far as the controls and the parameters are all set within the either the standalone control here or within the actual indoor unit itself. So you can really dial in a lot of detail into the operation of the heat pump with the controls that are integrated into these systems. So like right now, it's been in the 40s most nights, but I have our system set up so that the heat pump is not actually coming on to energize the buffer tank until it gets into the 30s outside. You can decide that you'd rather have the heat pump be available when it is in the 40s outside. So you can control, when the heat pump comes on or off based on outdoor temperature and variety of other factors you can come into play as well here too. So with this buffer tank, we have 40 gallons of storage capacity, thermal storage capacity, and a total of 20 kilowatt backup electric resistance that is available to back up the heat pump. It's just some of the other components of the system. We have room by room sensors in each room, sensing the floor temperature versus just the what the thermostat on the wall is seeing. So that helps equalize the temperature through the distribution zone by zone. A manifold where we're piping from, room by room loops, and outdoor temperature reset. So maintaining and controlling the system based on a sensor outside. That's tracking what the outdoor temperature is. The distribution type used in our system here is a Uponor Quick Track. It's a 1/2 inch thick plywood panels with aluminum sheets underneath them, with a track routed into those panels where the PEX tubing is embedded, so that this is directly underneath the finished floor. We have pine flooring installed over top of this. So the aluminum sheet that's underneath the panel, these plywood panels, is what helps reflect the heat from the tubing up towards the floor and helps to equalize the temperature across the floor as well. This is another example, one of Bill Chidsey's projects. This is the same SpacePack split inverter system, split refrigerant system. In this example here, Bill has 2 buffer tanks in play and a water heater. The reason there's 2 buffer tanks in this system is that the homeowner here was looking for cooling as well as heating. So there's different methods you can take with installing a system for cooling and heating. You can do it off of a single buffer tank, but more commonly it's going to be installed with 2. Because there may be times where you're going to be having a demand for both the hot water and the cold water side, especially if you have domestic hot water demand as well too. So it is more common when you have a system where you're going to be doing heating and cooling off of it to have a prioritized tank for cooling and a prioritized tank for heating. These were fan coil units in the wall panel radiators in the house. So this is just an example of what that looks like. The cover off. If you have a building that has a higher design load than what a single heat pump is capable of maintaining, then you can stage them as well. So that's what this is showing an example of, where we have 2 of the space pack split inverter systems staged to heat and do the primary heating for, or the sole heating for a larger house that has a higher design load. And so you see this in commercial settings a lot too, of staged systems and staged equipment.
Steve, we
yep.
are at time, so I don't know how many more slides you have.
This is pretty much it. So yeah, this is just to illustrate that there are, concern that's been raised is what happens when the power goes out. Just like any other system, though, if the power goes out, you're not going to have heating unless you have a generator. Like I said, these are soft start inverter driven equipment. So there are certainly generators that have the capacity to run a heat pump like this if the power is out. Again, it just comes down to matching system and equipment with what the need is. And then just finally, there's things coming down the line. There is some equipment from Sandon and Stiebel Eltron that do higher temperature water delivery in an air to water heat pump up to 149-degree delivery temperature. There's some limitations on what the outdoor air temperature is to how much capacity they have at that higher temperature. So it's not a drop-in solution still to existing legacy hydronic design. But there's more to come on that front. Advances and changes in refrigerants will also have an impact on the capacity of this equipment, but these are, a little bit further down the line. And the bottom line point to make to close out is really get the distribution system designed well and to optimize to the lowest temperature
Hi, this is
delivery
Lee-Ling.
possible. Hi, Lee-Ling. How's it going?
Are you there?
This is the spirit of Lee-Ling.
I know. Maybe that was accidental. Go ahead, Steve.
Okay. So yeah, again, the bottom line is get the distribution system right. And then no matter what technology or changes or advancements come down the line, you're going to have the best opportunity to integrate that into what is, again, an embedded asset of the building. So thanks for taking the time to be with us here today. I'm happy to stay on for a bit if there are